software library for modeling and simulation in solar desalination systems. www.redslibrary.com.
Hi everybody, first Mohammed Shah with you. Today we are going to talk about Parabolic Trough Collector design and performance models. As you can see here, we can select between two different models and make one model, but I do prefer to make it individual. We have design model for Parabolic Trough Collector, and we have performance Parabolic Trough Collector. Let's talk about design. This is our model, as you can see here. First of all, you have to assign some inputs. For such configuration, we are going to talk about three types of working fluids, and we can add more if we would like. We have water working fluid, thermal heat transfer oil, and we have here molten salt. And the same for performance model. Okay, for design Parabolic Trough Collector, let's double clicking here. Okay, if you have any kind of intention or to visit our YouTube channel, okay, you can assign solar radiation. Sure, you can replace this dynamic slider by editor. You can edit and just go to your mask subsystem parameters, and you can go here for solar radiation, and you can choose edit if you would like. You can choose edit. In such kind of inputs, you can edit transient if you would like. I mean by transient as can enter a matrix here. You can enter matrix, so suppose 5, 7, 6, and your results will become a matrix. Okay, but in this model I'm going for dynamic model. I do prefer this one. Okay, this is solar radiation. Suppose I would like to start at 200 watt per meter square, and this is ambient temperature. Suppose it's 25 as usual. Inlet fluid temperature. If you are going to use, you can choose from here, from this tab, your working fluid. If you are going to use a molten salt, suppose I'm going molten salt, so be sure that your temperature not be reduced below 150 degrees Celsius, because it's a freezing point for molten salt. So suppose I'm going for 180 degrees Celsius, and the output, be sure that suppose I'm going for beginning from 400 and so on. And we can control mass flow rate and hydraulic mass flow rate. This is hydraulic mass flow rate. It's a flow rate per loop. Suppose as a designer, I would like to make a 1 kilogram per second or 0.5 kilogram per second per each loop for the field. This is one segment, as you can see here in this photo. This is one segment. Okay. Suppose our mass flow rate is around 5 kilogram per second. Total field mass flow rate 5 kilogram per second, and our collector length is around total length of the field is 600. So suppose it's 500. You can control this, and you can make this a slider and choose effect of increasing the length of the collector. Changing the slider or editor, you have to right click here and go to mask and edit mask. Okay, choose parameter, and you can reform this the type of inputs, as you can see here. Let's get back again. Okay, and you can choose a collector with glass envelope diameter, inner tube, some hydraulic losses. Suppose it's 23 hydro losses through the tubes. Okay, I'm going for let's go for terminal or molten salt. It's up to you. I think we did a video before about the molten salt. Let's go and inspect terminal. Okay, terminal this is water, terminal, and molten salt. Let's go for terminal and see. Let's hit run. But before, we have to set our time limit or simulation time to infinity, and let's go and hit run and see. Okay, we can control from here. Yes, we can control from here. Okay, let's okay, but before, I'm sorry, before, let's hit stop. I have to assign some outputs before going to inspect for inspection. Okay, let's hit run and simulation time, hit run here and see. Okay, let's make some changes for the solar radiation, and we have to keep watching our this effect on the parabolic area. As you can see, increasing solar radiation will decrease, because it's a design model, will decrease solar field area, as you can see here. And I do expect such effect by reducing outlet temperature. Outlet temperature would decrease the solar field area as well. Suppose decreasing inlet temperature. Okay, and let's go for increasing the mass flow rate. Increasing mass flow rate sure would increase massively increase the solar field area, as you can see here, 100 kilogram per second, as you can see. Okay, let's hit stop and see our results. Okay, let's go here. Okay, suppose I need to inspect the effect of changing some parameters on the area. As you can see here, this is the area, and this is collector total feed length, parabolic trough efficiency, decreasing and increasing according to from 60% up to 70, around 70% as efficiency. A number of solar field per field. Yes, sure. If we increase solar radiation, there's some kind of decreasing in number of solar collector over the field, and if we increase this mass flow rate, therefore we need more solar field, number of loops as well, increasing total field flow rate, and this is inlet temperature and solar radiation. We already used this. Okay, this for terminal. Okay, suppose I'm going for these three types of working fluids. Suppose I need to inspect water. Let's go for water working fluids. Okay, and we are going to make some changes. This is our water. We are talking about a design model. Okay, yes, let's go and hit run and see our effects. That's for water. Okay, let's make some changing, decreasing. Okay, that's decreasing outlet temperature, decreasing inlet feed temperature. Okay, decreasing. Okay, down to maybe 50 degrees Celsius. That's fine. Up to outlet temperature, I think, well, we are not allowed to go for water up to 300, because we have to keep watching our evaporation pressure, because it may cause severe stresses on the tubes. Let's going for decreasing mass flow rate. It will decrease sure the field area, as you can see. Okay, let's go for increasing. Okay, increasing or decreasing, I mean controlling the operating conditions, and we can see the same effect on. I'm sorry, we have to go here. I forget to assign this. We can assign this by clicking on stream signals, and we can name this in order to keep watching this. I'm sorry, we have to do this, removing this semicolon. Okay, we need to discover collector field area as well. Okay, total field length. Okay, number of loops. Okay, and number of solar collector. Okay, let's hit run again and see. Okay, let's closing this one, and double clicking. We're inspecting. Yes, for water. Okay, water no more than suppose I'm going for 200, and inlet feed is 50. And solar radiation is, let's go for 400. Hit apply. Let's hit run. Going for water results, and we can compare our results. Let's compare our results by changing solar field, solar radiation, watt per meter square. As you can see here, decreasing the design parameters, and you can go transient as well. Suppose I'm going for 200, and let's go up to 290. It's okay. Increasing inlet feed temperature would help in decreasing or increasing the efficiency. If you increase inlet feed flow temperature, would increase the efficiency of the solar field. Let's go for mass flow rate, high mass flow rate up to 150 kilogram per second. And let's hit stop and see here. Okay, this is terminal, as you can see here. This is the results of terminal before, and this is our water. Let's go for area. As you can see here, you can put, this is water, and this is terminal. As you can see, for collector total length, this is water total length against terminal, and you can inspect also molten salt as well. Three figures, three curves on the same figures. It's quite interesting. Okay, let's go for number of solar collectors. Number of solar collectors, yes. Sure, using water working fluid is much greater than number of loops. Okay, so I forget to do this. I'm sorry. I have to do this. Yes. Okay. That's for design model. Okay. Let's hit. Okay. For performance, it's a little bit quite different. For performance, we have to, this is our performance model, as you can see here. For performance, we have to inspect the feed mass flow rate, the flow speed. It's quite different, a little bit different. Area pressure is already, you have to enter. I mean, this parameter is known, aperture area or receiver area or cover area, and we can calculate the compression ratio. We have to calculate cover temperature, receiver main temperature, and outlet collector temperature, and this is mean fluid temperature. Mean fluid temperature. And we can some performance analysis we can calculate, such as efficiency factor, flow factor, heat removal factor, and overall heat losses, thermal power, thermal efficiency, and this error percentage between estimated and assigned results. Suppose I'm going for let's go for set our solution time into infinity. Okay, I'm sorry, and let's go for I think terminal. Okay, let's go trying terminal. Okay, and we have here for operative conditions, solar radiation, ambient temperature 25 as usual, inlet fluid temperature. This is inlet fluid temperature to the solar field. I think it's 100. Quite good. And this is flow, number of loops. Here we can assign number of loops. In design model, we have to calculate number of loops, but here because performance, it's already existing plant, so we already know our loops. We already know our width, parabolic height, collector length, focal length, as you can see. Let's go for suppose it's 1 meter, and total mass flow rate, suppose it's around let's beginning from 1 kilogram per second, and some inputs. Okay, we are inspecting terminal. Okay, this is performance. Let's go for terminal working fluid and see our results here, but before we have to go in here and selecting and stream selecting signal to data inspector. Okay, this is our data for inspector. Okay, okay, let's keep watching our results, especially on temperatures. Okay, let's go here, and we have to do this. We can make some changes. Keep it at 2, and let's go for terminal, and here we can hit apply. Let's hit run and see changing some solar radiation. What is the effect on temperature? Okay, changing solar radiation will change outlet temperature, outlet parabolic trough temperature, as you can see here, and of course effect of ambient temperature as well, and inlet fluid temperature. Let's go for increasing. Okay, okay, increasing mass flow rate. Okay, increasing mass flow rate would decrease the temperature, of course, because of heat removal factor. Okay, increasing solar radiation. Okay, increasing inlet feed temperature. Okay, this results at 600 feed lengths. Okay, that's it. Stop, and you can see here. You can keep watching your results as well. Okay, let's go here, and this useful energy changing here. The thermal power from the solar. Yes, from here. Is a fluctuation of thermal power, and this is mass flow rate changing. Outlet mean feed temperature. This mean feed temperature. Efficiency factor changing. Flow factor, as you can see here. Here's heat removal factor. Let's go for not exceeding over 1, by the way. And we have thermal efficiency, changing in thermal efficiency. You have Reynolds number of this solar field area, and receiver mean temperature. This receiver mean temperature, as you can see, decreasing and decreasing. Lit flow temperature as well. So we are glad to say that we have Parabolic Trough Collector model. We have design model and performance. For performance, you have to calculate this efficiency of. You calculate some performance parameters such as efficiency, overall heat losses, flow factor, efficiency factor, heat removal factor, and the outlet temperature as well. We have to assign outlet temperature. We have to calculate outlet temperature. However, in design model, it's input. Outlet temperature is still remaining as an input, not a result. And we can assign the efficiency by changing, by using empirical equation for it, for the design model. So you can compare between design and performance, and you can use your results based on different working fluids. You can select your working fluids from here. You can make your selection by using water or terminal or molten salt. It's quite easy for you, and you can changing some inputs in order to realize their effect on the outputs. Finally, would like to thank you. Don't forget to like, share, subscribe, and thank you very much. Let's label the call.